from last video, we saw that the L1 of G is actually a Banach algebra. Basically, we put a convolution on the L1 of G. The convolution just acts as a multiplication on this Banach algebra. And we saw it has basically joint continuous. And now we just want to put more structure on the L1 of G. And in this video, I want to show it's actually a Banach star algebra. Basically, we need something called a involution. So just recall from what we had in the modular function. If I want to integrate the f of x respect to the left Hard measure mu, then I can also do the integral of the f inverse, but I need to compensate by adding this this modular function here. So that's kind of the formula we prove from when we talk about modular function. So that kind of motivates us to do the definition of an involution. So recall that the involution in the Banach star algebra needs to satisfy a bunch of things. For example, it needs to be the double involution is give you the original function back. It needs to be conjugate linear. And when you do the AB involution of AB, then it's the B involution times the A involution. Okay, so that's kind of the idea. And most of the time you do want your involution to be isometric. Okay, so just based on this formula, you kind of guessed what the involution looks like. So let's define the following. I don't want to put a star, so I think that's also Nico used this notation, the f check, to denote the involution. So what it does is the following. So it evaluates the fx inverse, and you also need to multiply the modular function of x inverse. But you also want to make it conjugate linear. So the modular function is a real value, so that doesn't really matter. But the f is complex value, so let's put the conjugate in there. Right, so this is going to be our involution on the L1 of G. And it's fairly clear just based on the formula above that the integral of this f check, if you put the absolute value there, doesn't give you the same kind of the integral of f. So let's just put it as a little lemma maybe. So if your f is in L1 of G, then your f check is also inside the L1 of G. And moreover, the one norm is going to be the same. Okay, so that's kind of trivial from the formula we have. All right, so the idea is now this involution together with the convolution we defined put a Banach star algebra structure. So L1 of G, the theorem we are proving now is that it's a Banach star algebra. And under the convolution and involution we defined. We already saw it's a Banach algebra from last video, so let's just prove it's an involution, it's a star algebra. So I need to show, first of all, when I take any function, I do the double check. Okay, so this by definition, if I evaluate at x, this is the f check evaluated at x inverse, and I take the conjugate of that, and I need to multiply the modular function at the inverse. And you do the same thing for the f check x inverse that give you by definition. That's the f of x conjugate modular function x, the whole thing conjugate, and multiply by x inverse, the modular function of x inverse. And the modular function is real valued again, so the conjugate of delta x is just delta of x, and delta is a group homomorphism, so delta x inverse multiplied to 1. And that's fairly clear, this end up as f of x. Okay, so the double check is f itself. To check is conjugate linear, that's just trivial. I'm not going to do that. Let's just say trivial. And lastly, I need to say, let's consider two functions, say f and g, and I consider their check. Okay. So by definition, just use the definition I have is basically their convolution evaluated at x inverse, the whole thing conjugated and multiplied by delta x inverse. And let's recall the formula for the conjugation. So this is the integral of what we have is, first of all, let's say we conjugate f and g, but evaluate at the this x inverse. So let's put x inverse y and then g of y inverse. Everything is basically conjugate. Okay, so let's conjugate. So this is the d mu of y. And then we also have a delta of x inverse. So let's do the following. So let's move the this whole conjugate inside, and then let's move the modular function inside as well. Okay, so let's keep this one in here, d mu of y, and then I have a bunch of conjugate here. All right, so basically now I want to write it as some integral of, well, basically I want to reverse the y and y inverse. Okay, so what I do is that I can do the following. So I can try to find the involution of f and g. Okay, that's what I need to find. Okay, so first of all, let's do the following. So let's do f of x inverse y. If I want to do the involution of f, I need the delta of x inverse of y. Okay, let's just put a delta of x inverse of y here. And because I only have a delta of x inverse, okay, so now I have a delta of x inverse y, so there's an extra copy of y. So I need a delta of y inverse somewhere, and if it's perfectly, I have a g of y inverse conjugate, okay. So the first thing evaluates to basically the f check evaluate at x inverse y. And the second one just equals to the g check evaluate at here is y. Okay. All right. So sorry, the first one should be this one, the entire thing inverse. Okay, so the entire thing inverse dy. Okay. So in this way, we basically move the y back to the inverse, and let's just write it out. Again, this is f check of y inverse x. And then I have a g check y, d mu of y, and you can just move these two around. This is g check of y, f check of y inverse x, and this gives you the conjugation, the convolution of g check and y and f check. Okay, so if you check the formula, this is g check convolute with the f check. So the conclusion is, if I want to convolute two things, I might do the involution afterwards. I can do the involution first, but in the reversed order. Okay, so this is basically the last thing we need. All right, so this finished the proof of this Banach star algebra structure on L1 of G.